Swayam Prabha. Digital India. Educated India.
Welcome back. Let's continue our discussion on turbulent combustion, and we are discussing now combustion and thermochemistry, and where we stopped in the last class when we are having a reacting system with multiple species. So, we looked at different properties and how to calculate them, and we stopped where we looked at the calculation of the total pressure. So, this is where we had it, the total pressure would be the summation of all the partial pressure, where Pi is the partial pressure. So, that is how you get the total pressure of the system. So, this will give you the total pressure of the system. Now, and partial pressure of ith species. So, individual species partial pressure is summed up to get the total pressure of the system. Now, how partial pressure we can find out, or rather we can find out in a from partial pressure, if we know the total pressure of the system, then we can actually find out the partial pressure of that individual species. So, for to find out that, where you know the total pressure, you can find out with the mole fraction into total pressure. So, that will get you the partial pressure of the individual species. Now, for we are dealing with the ideal gas mixture. So, for ideal gas mixture, you can get the mixture enthalpy, which will be summation of all the species over I multiplied with the individual mass fraction of that species into Hi. So, let us continue at the similar notation of the equation system. So, this would be 1.15 A, and the mean would be for the mixture is summation over all the species Xi and Hi bar. So, this is 1.15 B. So, that is how you get individual these things. Now, similarly you can find out the entropies. So, for example, entropy is a function of temperature and pressure. So, that will get you, if you get summation over all the species I, then mass fraction of individual species Si, temperature, pressure. So, that you say 1.16 A. Then similarly you can find the average entropy, which would be again similarly like over all the I, Xi, average entropy, and that would be your 1.16 B. Now, pure species entropy depend on the species partial pressure, which you can see from this above equation. So, you can use this and get the different. Now, if you take a reference state, let us say reference state is P naught, which is 1 atm. So, if you take a standard state, that also one can say this is an standard state. So, and that is what you take as a reference state, and you calculate Si for a particular partial pressure Pi, which will be Si T for a reference pressure minus R ln Pi by P reference. That is what we are actually to some extent doing the revision of our basic thermodynamics along with the combustion. So, this would be 1.17 let us say A. Then the average one you can find out for T P I would be average T at P ref minus R U ln P I by P ref. So, this should be, one can look at the individual calculation of these species and their entropies and all these other properties. Now, there would be another thing is that latent heat or enthalpy of vaporization. So, this is important when the liquid actually vaporizes. So, for example, let us say P is constant pressure process, then HFG would be heat required. So, that is heat required to completely vaporize a unit mass of liquid at a given temperature. So, this is a constant pressure process and HFG is the amount of heat which is required to completely vaporize a unit mass of liquid at a given temperature. So, what we can get HFG equivalent to H vapor at a given temperature and pressure minus H liquid given temperature pressure. Now, one of the famous relation is Clapeyron equation, which gives you an equation for saturated pressure with the enthalpy dT by T saturation square. So, this is what you get from the Clapeyron relation, and that is what you can get and find out the amount of heat required or the enthalpy of vaporization. So, now we move to the first law of the system. So, again this is again the revision of thermodynamics. So, first law of the thermodynamics which talks about essentially the fundamental principle of conservation of energy. So, it talks about the energy for a isolated fixed mass system. So, if you look at the finite change between two states 1 and 2, so this is the equation which comes out of the first law or energy conservation. So, that is the heat added to the system. So, we follow some convention, and if heat is added then it is positive. So, if this is the system, it heat added, this would be positive. If it is work done, that would be positive. So, this is work done by the system is the change in the energy of the system. So, that is the delta E. So, one important thing to note here, both this heat and work, they are path functions. So, there are two different kind of functions that you come across. There are few which are point functions, but this is heat and work, these are essentially the path functions, and this will only occur at the system boundary. So, that is very important, that where does it occur, and that is the difference between total energy of the system. So, one can write the energy is a collection of all other energy. So, system, so you can have the internal energy, you can have the kinetic energy and the potential energy. So, this will get to the total energy of that particular system, and you have that system. Now, one can write the equation, the first energy balance equation for unit mass basis. So, one can get there are two ways one can write, either unit mass basis, then the difference between two state is the small q12, work done by the system small w12, and that is the change of the energy. See, this is still your first law, energy conservation, and same thing if one write in, this is in rate form. That means with respect to time, if someone writes that energy balance, so this is the amount of heat transfer takes place across that system boundary, then the work done across that system boundary, or rather at a rate of that system boundary, and then this would be the change of the system energy. So, that would also with respect to time you get it, and if you write per unit mass, this is in rate form per unit mass, the energy conservation principle. Now, if we extend this one, this first law analysis for the control volume system. So, these are again refreshing the memory of our thermodynamics, because these are essential component of the detailed analysis what we are going to do later stage of this course. So, control volume analysis, you say steady state, steady flow from the first law. Then you have an control volume which is defined, and across that control volume, this is your control volume, then you find out the rate transfer, this is the heat rate, this is the work, then rate of energy flow into the control volume. So, there would be a flux, change in flux. So, something comes in, something goes out. So, let us say E dot I comes in, E goes out with a mass. So, when you come to the control volume, there is a mass crossing the boundary, then m dot net rate of the work associated with the pressure forces. So, that you take into account, then you get this equation for your steady state. So, there are certain assumptions which are associated with these particular equations. One of the important assumption is that the control volume is fixed relative to the coordinate system, that means that is not moving. So, once you have a fixed control volume, that means it is fixed in space. Then the properties within the control volume, they are not varying with time, and that is why we assume it is an steady state. So, that means within that they are not changing with time. Also, fluid properties, they are uniform over inlet and outlet areas, and you have only one inlet and one outlet stream. So, these are some of the assumptions that we have to come to this particular equation for a control volume. Now, we can use the specific energy for the inlet and outlet stream, and what does that have? So, as we have seen that specific energy, the total specific energy per unit mass will have a one component from the internal energy, that is one component. If one of these particular part of the component is not present in a system, so that will not contribute, otherwise the total energy or total specific energy should be coming from internal energy, kinetic energy and the potential energy, and where your V is the velocity stream crosses the central control volume, then this Z is the elevation where steam crosses the central volume, and G is the gravitational acceleration. So, these are standard terminology which are used. Now, similarly, you can define other properties like enthalpy. So, specific enthalpy would be internal energy plus pressure into volume. So, which you can write U plus P by rho. So, then the previous, if you couple previous equations like 1.25 to 1.27, if you combine all of them, which will essentially get you Q dot Cv minus W dot Cv equals to m dot H naught minus Hi, that is inlet and outlet state, plus half of V square minus, this is velocity, Vi square plus G Z0 minus. So, difference of two different state. So, again this is then including all the masses. If you look at per unit mass, so this will be represented as QCV is a WCV equals to, or you can take this one on the other side, and H naught minus Hi plus half V naught square minus Vi square plus G H dot minus Zi. So, which will be your equation number 29. So, you can write using the, you can bring in this enthalpy into the picture, which will make your life quite easier. Now, if you move ahead and look at these things, the reactant and the product mixture. So, one thing that we want to define is the stoichiometry. Now, the stoichiometric quantity of oxidizer, when you say that a particular reaction is a stoichiometric reaction, so you can see this is one hydrocarbon which is burned with air, then you get CO2, H2O and excess nitrogen, if nitrogen being an inert gas. So, you can find out the balancing and get those numbers A, X, Y, everything, and when you say that the equation is stoichiometric, that means it is an sufficient, or it is an balance between oxidizer and fuel which is required to, for a particularly this compound to burn with the air, that A amount of air is required which is enough to burn the completely fuel. So, air fuel ratio you can find out the stoichiometric air fuel ratio, let us say for which it would be m air by m fuel, that is 4.76 A by molecular weight of air by molecular weight of fuel. The equivalence ratio, which is defined as an air by fuel stoichiometric by air by fuel actual, or one can write fuel by air actual by fuel by air stoichio. Either way they would lead to the same set of expression, and then you say phi greater than 1, that would be one condition, phi less than 1 would be another condition, phi equals to 1 would be one condition. So, obviously, when phi equals to 1 means that is my actual fuel air ratio and stoichiometric fuel air ratio, they are same. So, that means it is a balanced amount of fuel and oxidizer are there to have a combustion to take place. So, this is your essentially stoichiometric mixture. Then when phi less than 1, you will have fuel lean mixture, and automatically this would be fuel rich mixture, and one can look at from the equation that we have derived here that what would be corresponding. Now, another thing is that percentage of stoichiometric and percentage of excess air. So, that is another definition, percentage of stoichiometric air equals to 100% of divided by phi. So, this is, and percentage of excess air would be 1 minus phi divided by phi into 100%. So, this is what you can get. Now, second important thing is that absolute enthalpy, and so that is one important terminology is absolute enthalpy, another is the enthalpy of formation. Now, absolute enthalpy is sum of an enthalpy of formation and sensible enthalpies. So, this is how we get, that means this is my total absolute enthalpy at a particular given temperature T. So, that will have two components. One component would contribute from the enthalpy of formation of a particular species, that is why I comes here into this particular system or equation for a particular T reference, and then the sensible enthalpy component, which is nothing but the energy required to have a change from T reference to T. So, to go from one state to, and this is the energy change or enthalpy change, and that would be at a particular T which is of concern, the enthalpy at that state minus enthalpy of formation at reference state. So, this is how one would get these things. Now, how we define? We can define the standard state, typically 25 degree centigrade and reference temperature pressure 1 atmospheric. So, enthalpies of formation are essentially 0 for the elements in their naturally occurring state at the reference temperature and pressure. For example, at 1 atmospheric pressure and 25 degree centigrade, oxygen exists as a diatomic molecule. So, the enthalpy of formation is 0. So, there are plenty of similar things, I mean similar species like nitrogen, hydrogen, other available, and one can refer to any of these textbook to look at the enthalpy of formation. Now, what you talk about absolute enthalpy. So, the absolute enthalpy is the, to form oxygen atom at the standard state requires breaking of chemical bond, and the bond dissociation energy of oxygen at standard state is this. This is a standard information one can. So, the breaking of bond creates two oxygen atom, therefore, the enthalpy of formation of the oxygen is this. So, what you get the enthalpy of formation is that to break this O to two O atoms. So, this is the energy which is provided to break this bonding, and you get the atoms here, and that is what the enthalpy of formation is. So, you can think about the enthalpies of formation is the net change in enthalpy. So, one can write in really in text the net change in enthalpy which is associated with breaking the chemical bonds of the standard state elements and forming new bonds to create the compound of interest. For example, at standard state nitrogen, hydrogen they are 0, but if you look at N or hydrogen atom there are some enthalpy of formation. So, this is piece of information one can get in a book. So, this is one of the graph which shows you or gives you an idea that this side your absolute enthalpy, this is your temperature variation along these things. So, this is oxygen molecule, this is oxygen atom, and you can get the different situation. This is your enthalpy of formation and this is the change of state which is shown by that curve. Now, we move forward to look at the heating values, or something which is very common in combustion process is the enthalpy of combustion. So, you have an system like this isn't you think about a steady flow reactor. So, there are reactants which are coming in through this inlet and the products which are going out of this outlet, where you assume there is a complete combustion at standard state. That means, the products which are going out, they are the outcome of the complete combustion, and reactants which are coming, they are at the stoichiometric standard state. Now, as I said, stoichiometric mixtures, the reactants at standard state, products are the product of complete combustion. That means, there is no excess fuel, neither excess oxygen or air which is oxidizer present there, but that also comes out at the standard state. Now, product to exit at the same T and the reactants, heat must be removed. So, this is what exactly shown there, because the reactants are coming at standard state and products are also coming out of standard state. So, that means the temperature, but there is a reaction or combustion takes place here, and when there is a combustion takes place, there would be a amount of heat which is produced. Now, that should be removed from the system to maintain that. So, that would be related and product of the absolute enthalpy, and one can use the first law here to find out that. So, the amount of heat which is there, that is a difference between enthalpies of the outlet and the inlet. So, that is the product enthalpy and the reactant enthalpy. Now, the enthalpy of reaction or enthalpy of combustion, so that is per mass of mixture, one can say delta HR, enthalpy of reaction, is equal to the amount of heat which is taken out of that particular control volume. So, that would be the difference of my enthalpy at the product state and the enthalpy at the reactant state. Now, in terms of extensive properties, so if it is not per unit mass, so that is the delta HR, which is the difference of your absolute enthalpy and the difference of reactant enthalpy. So, we can take an example and see what happens. So, let us say at standard state, the reactants of stoichiometric mixture of methane and air, where 1 kilomole of fuel reacts is this. Now, at the same condition, the combustion product have an absolute enthalpy of this. So, you get the delta HR or enthalpy of combustion. So, that is your enthalpy of reaction or combustion, whatever you call it, that is product absolute enthalpy minus reactant. So, this will be the amount that you get. So, you can adjust this value to a per unit mass of the fuel. So, one can write delta HR per unit mass of fuel, which is delta HR per molecular weight of fuel. So, that you can get, or you can write delta HR, which is per unit mass of fuel equals to minus 82405 divided by 16.003 or 4, whatever it is. So, this would be 50.016. So, that is how you can calculate it. So, we will stop here and we will continue in the next lecture. Thank you.